In this set of notes, we're going to look at probability distributions by making tree diagrams. And a probability distribution, again, is all the possible probabilities for a given situation. So let's look at a situation where we want to state the probability distribution of having boys in a family of 3 children. All right, so we first want to figure out what does this look like, and we can do this by making this tree diagram. Again, for some people, tree diagrams may not be needed because you can see what's happening, but for most of us, probably making that tree diagram first is helpful, and then we can make that probability distribution after that. So here is our family, and this is what the tree diagram is going to look like. So on our first child, we can have a boy or we can have a girl. And the probability of having a boy is 1/2. The probability of having a girl is 1/2. So that's the first child. On the second child, we can have, if we had a boy the first time, then we can have either a boy or a girl the second time. Again, this is either going to be a boy or a girl. Or if we had a girl the first time, again, we could either have a boy or a girl. These are independent events. One is not affecting the other. Remember, with independent events, we also have, or I guess these are not non-overlapping events because they're ors. We've had a boy and a boy, or we had a boy and a girl. Or we had a girl and a boy, keeping in mind how important the ands and the ors are. Or we had a girl and a girl for our second child. So there's these different situations, a boy and a boy and a girl first, then a girl first, and then another girl for our second child. Now when we get on to our third child, again, if we had a boy as our second child, we could either have a boy or a girl. These are again ors. If we had a girl for our second child after having a boy, again, we could have either a boy or a girl. If we had a boy after having a girl, we could either have a boy or a girl. And lastly, again, we could either have a boy or a girl. If we had a girl first, another girl. Now, a boy, and another boy. So each one of these branches, again, is an and statement in between our or statements. And this is going to come in handy in terms of us writing out our probability distribution. Remember, with and is multiplication or is addition. Okay, so here is what our probability distribution looks like. So again, probability distribution has to come up with all the possibilities. So we could either have 3 boys or no girls. That's one possibility. We could have 2 boys and 1 girl. That's a different possibility. We can have 1 boy and 2 girls, or we could have no boys at all, which would mean we had 3 girls. So keep in mind that the order does not matter here. Okay, so it doesn't matter if I have 2 boys first and then a girl, or I can have a boy and then the girl and then another boy. Okay, so the order does not matter. So now let's calculate this probability. So if we go back, if we're looking for 3 boys and no girls, that's this first branch here on our tree. So it's 1/2 and 1/2 and 1/2. If you recall from and statements are multiplication. So it's 1/2 times 1/2 times 1/2, which is 1/8. 1 times 1 times 1, 2 times 2 times 2. 2 boys and 1 girl. It says there's 3 branches of 1/2 times 1/2 times 1/2. So let's see here. So we have, it says 3 branches of 2 boys and 1 girl. So I'm going to just kind of circle There's one branch here. And then I have a boy, a girl, and a boy. So here's a second branch. And then I have, let's see, a girl, a boy, and so a girl, a boy, and a boy. And so I have three branches of 1/2 times 1/2 times 1/2, which would be 1/8 or another 1/8 or another 1/8. If you recall that each one of these in between is an or statement, and so we're adding those up. And so 1/8 plus 1/8 plus 1/8 is 3/8. One boy and two girls. Again, there's going to be three branches of those, so that's 3/8. And then no boys are all girls, which is one girl and another girl is 1/2 times 1/2 times 1/2, which is this piece right here, 1/2 times 1/2 times 1/2, which is all girls, which is 1/8. And then our probability distribution, our total has to be equal to 1. Because that captures all the possibilities that we have. So 1 plus 3 plus 3 plus 1. So again, when we multiply fractions, we multiply numerator times numerator. When we and then denominator times denominator. When adding fractions, we add all the numerators together, provided that there's a common denominator. And these tables will always have a common denominator because we're going to be working with the same probabilities for each one of them. So let's look at something that's a little more complicated. So now we're going to eat 2 M&Ms out of a bag containing 2 green, 4 red, and 3 blue M&Ms. And now we want to find all the possible probabilities for pulling out and eating the blue M&Ms. So again, making a tree diagram is helpful. So we have 2 green, 4 red, and 3 blue. So let's let me just go back. Let's see, 2 green. Just write these down. 2 green, 4 red, and 3 blue. All right, so that's what's in our bag. So we have 9 candies in our bag, total of 9 in our bag to start with. So the first time we stick our hand in there, our first draw, we can either get a green, or we can get a red, or we can get a blue candy that came out because there's 3 different colors. Well, the probability of getting a green would be 2 out of 9. Probability of getting red would be 4 out of 9. Or the probability of getting a blue one would be 3 out of 9. Okay, so that's the first time. Now we're going to eat 2 candies, so we got to go stick our hand in there again. Now, because we're eating the candies, now we have dependent events. And so, again, these are and statements. So it's dependent. So we're going to have one affect the other. So now that we've eaten the green candy, we'll pull out another green one. Now we only have 1 green candy, and now there's only 8 in the bag when there was 9. But let's suppose, or I don't know what just happened. So let's suppose that so we still have that or. So let's suppose that we pulled out a green one, ate it, but next time we pulled out a red one. Keep in mind that there's still 4 red candies, but only 8 left because we ate the green one first. Or we pulled out the green one, and this time we pulled out a blue one. Well, we still had 3 blue candies because we pulled out a green one the first time, so there's still 3, but we only have 8 candies because we ate the green one. So as we go through this, if we pull out a red one first and then a green one, there's still 2 green candies in our bag because we ate a red one first. None of this has happened, okay? So we're only focused on what's happening here in this section here. So we pulled out a red one first. We still have 2 green candies, but we ate the red one, so there's only 8 candies left. Pulled out a red one, ate it. Now I only have 3 red ones left out of the 8. Ate a red one. This time I pull out a blue one. I still have all 3 blue ones. All right. So now we want to make that probability distribution. And we wanted to have a probability. Remember, we wanted a probability of blue M&Ms. So we either are going to have 2 blue M&Ms or nothing else. We're going to have 1 blue M&M of either and 1 other. It's either going to be red or green or red. Or we're going to have no blue M&Ms, which means they're going to be the other colors. So they would either be green or red. And you can see as we go through, and I color coded these so that you can go back and look at each one of the branches. And again, an and means we're multiplying, an or means we're adding. And so for 2 blue M&Ms, there's only 1 branch down here, 2 blue. But for 1 blue and 1 other color, we have a blue and a red. We have a blue and a green. We have a red and a blue, and a green and a blue. So there's 4 calculations that you'll see here, each containing at least 1 blue. And then we have no blues, and again, there's 4 calculations for that.